Welcome to the second video lesson in this series on the particle model of matter. In this video lesson, we're going to look at what happens to the particles of a substance when they are heated and when the substance is cooled. We're also going to look at an exception to the rule, that namely of the anomalous expansion of water. And then we're going to look at phase changes. What is a phase change and the types of phase changes, and how to represent the change in behavior of the particles in a substance as the substance undergoes the various phase changes. So let's start off with what happens when you heat matter. Now, when you heat matter, you're adding heat, which is basically energy. It's the transfer of energy, which adds to the energy of the particles. So that means the particles start to move faster. And the faster they move, the more the particles will collide into each other. That means that the spaces between the particles become bigger. And that means that the substance expands. Now notice that I have circled the word particles. And that is because it's extremely important in a test and an exam to use the word particles. Sometimes learners will answer the question of explaining what happens when you heat matter according to the particle model, and they'll do it beautifully. They say adding heat adds energy, and this means that things move faster. And they don't use the term particles, and so then they lose marks. So remember, we're investigating, or we're learning about the particle model of matter. The particle model of matter, so we must always use the word particle or particles. So what happens when you cool matter? Well, cooling removes energy from the particles, okay? And the particles therefore start to move slower, which means that the particles are going to collide less into each other, and therefore the spaces between the particles become less, and so the substance contracts. So the general rule is that when you heat a substance, it expands, and when you cool a substance, it contracts. And that is the general rule. However, there is an exception. But before we look at the exception, I once again want to refer to the following. And it really is important to know what not to do as well. When matter is heated or cooled, the particles do not change in size, but rather the spaces and the velocity of the particles change. So the spaces between the particles change. Now, let's talk about water. So water is an amazing substance, and it is the only non-metallic substance that expands when it freezes. Now, this is an exception to the rule. We've just explained why substances will expand when you heat them. And it makes sense. You're going to increase the speed of the particles, therefore they're going to collide more, therefore they're going to, the spaces between them, the average spaces between them are going to increase. But in water, and you might have experienced this, if you take water and you put it into a bottle, which I do not suggest you do, and then you pop it into the freezer, that bottle's going to pop. And the reason is that when water reaches its freezing point, where it changes from a liquid to a solid, the solid is actually going to expand, and therefore the bottle will explode. It's not a good idea to do it with a plastic bottle, but it's definitely not a good idea to do it with a glass bottle, because that's going to mean there's going to be glass all over your freezer. So there has to be something else at play. And what's happening here is that on a molecular level, there's a special type of bonding that takes place, which is called hydrogen bonding. And this occurs between the water molecules. And it results, as I'm going to explain now, soon enough, that the molecules, in order to come close together, actually end up taking up more space. So here is a diagram that shows what happens. So you have these very special forces, which you will learn more about later on in your high school science courses, that exist between the water molecules. And when they freeze into ice, what happens now, they actually form these hexagonal, six-sided crystal cells. but they take up more space, and therefore the ice expands. If the ice expands, then it means its density decreases, and therefore ice is less dense than water, and therefore ice floats on water, which actually plays a major role in the oceans and in lakes, because by the ice floating on the top of a lake, it actually insulates the water underneath it so that the fish and other animal life can actually live in it and not freeze. So now let's look at what is hydrogen bonding. So this is not going to be asked explicitly in a test or an exam, but I would like you to have a basic understanding of what a hydrogen bond is. So if we look at two water molecules, a water molecule, water is H2O, so there's two hydrogens and one oxygen. And for reasons that we're not going to go into in grade 8, the hydrogen side of the water molecule is more positive than the oxygen side. And so what happens when two water molecules are close together, the positive side of the water molecule, the hydrogen side, gets attracted to the negative side of the water molecule, which is the oxygen side. And so there's this very special attraction that takes place called hydrogen bonding. Now, when you cool water and it gets to around about 4 degrees Celsius, these water molecules start to rotate and form a special arrangement where you can see here the oxygen side of the molecule is attracted to the hydrogen side, so the negative to the positive, but they arrange in such a way to form this 6-sided pattern. And this is known as a crystal cell. And as the water cools to around about 0 degrees, an ice crystal forms. But this space inside each ice crystal cell results in the water expanding. So in a test or an exam, we will ask you, for example, can you give us an exception to the rule of how substances react when they are cooled? And that would be water. And we could maybe ask you, what is the cause for the anomalous expansion? Now, anomalous is a fancy word, but what the anomalous basically means is strange or doesn't make sense. An anomaly is something that doesn't make sense. And science's task is to explain these anomalies. So the next thing we need to look at is what we call phase changes. So we're going to look at the different states of matter. Now, you can refer to the states of matter or the phases of matter. It's fine in grade 8. But when we talk about the phases of matter, we're talking about solids, liquids, gases. There are a few other phases we'll still refer to. But states of matter can actually be a broader term. But in grade 8, we'll use states and phases to have the same meaning. So we are going to look at what happens when a substance goes from a solid to a liquid, from a liquid to a gas, or from a solid directly to a gas. Now, these phase changes, some of them we see regularly. So, for instance, if we take water and then we heat it up, eventually water will go and become steam, and so that will be evaporation or boiling. Okay. If we take ice and we add heat, it's going to melt and become a liquid. But there are some of these phase changes we don't see regularly, and we're going to talk about that soon enough. So let's now take a look at what happens when we heat and when we cool a substance. So we are going to look at, when adding energy, how the solid becomes a liquid, becomes a gas. And now when we remove energy, the gas becomes a liquid and then becomes a solid. Now, this is very important, and these definitions you need to know. So first up is the definition of a phase change. So a phase change is a process. A phase change is the process where a substance changes from one phase or state to another phase or state when heated or cooled. And that is a very, very important definition that you need to know. Now we get different types of phase changes. So for instance, melting is the process where a substance changes from a solid to a liquid when heated at its melting point. Now, if we're dealing with a pure substance, in other words, we're dealing with something like water or carbon dioxide, we're not dealing with, for instance, salt water where there's water and a salt. We're not dealing with mixtures. We're dealing with pure substances. Then there is a specific melting point. Now, what is the melting point? The melting point is the temperature where a substance changes from a solid to a liquid. Now, we are going to ask you these questions in tests and exams, and these little ticks represent marks. So if I ask you what's the definition of melting, there's going to be a mark for the fact that you say it's a process. So that tick there is for process. And then there will be another mark for stating that it's when it changes from a solid to a liquid when heated at its melting point. There will be another mark. Now, when we talk about the melting point, it's the temperature where a substance changes from a solid to a liquid. Now, sometimes learners will say it's the point where a substance changes from a solid to a liquid. Now, you are not going to get the mark for point because we are asking you to explain what does the melting point mean. So you can't use the same word to explain the concept. You've got to use a different word. So the point is referring to a temperature where a substance changes from a solid to a liquid. So let's now look at the other phase changes. So boiling is the process where a substance changes from a liquid to a gas when heated at its boiling point. The boiling point is the temperature where a substance changes from a liquid to a gas. We're all familiar with boiling. Freezing, we should also be familiar with. Freezing is the process, you see, it's the process where a substance changes from a liquid to a solid when cooled at its freezing point. So these definitions are normally 2 marks. The freezing point is the temperature where a substance changes from a solid to a liquid. That would be the other mark. Now, condensation is the process where a substance changes from a gas to a liquid when cooled at its condensation point. We sometimes see this in winter when it's very, very cold and we climb into the car and we breathe out in the car. Very soon there's condensation that forms on the inside of the windscreen, and that's because the water vapor coming out of our bodies from the breathing is suddenly cooled to a point where it goes from being a vapor, a low pressure gas, to a liquid. The condensation point is the temperature where a substance changes from a gas to a liquid. Now, sublimation, this is an interesting one. This is one that we don't really experience readily. And so what I'm going to do here, I'm going to move on to a demonstration that I will do with you in class, and that's namely the sublimation of iodine. Now, please note that not all substances sublimate, but iodine and carbon dioxide, commonly known as dry ice, are 2 substances. They're not the only substances, but there are 2 substances that do sublimate. So we're going to look at sublimation as the process where a substance changes from a solid to a gas directly without going through a liquid phase when heated at its sublimation point. The sublimation point is the temperature where a substance changes from a solid to a gas. And then we're going to look at the reverse process. Deposition, also known as recrystallization, is the process of where a substance changes from a gas to a solid when cooled at its deposition point. And then the deposition point or recrystallization point is the temperature where a substance changes from a gas to a liquid. So I also want to direct you to the YouTube clip that I have on our Pi site, which shows you this demonstration where iodine crystals are heated in a test tube and then they sublimate into almost a deep purple blue gas, and then when they cool as they go up to test tube, they recrystallize again. But let's look at these phase changes visually. So this is a very important diagram that you will encounter frequently in tests and exams. And so what this diagram does is it summarizes the various phase changes that we are covering in the grade 8 syllabus. So we have a solid, a liquid, and a gas, and I have taught you how to draw the particle diagrams of the three different phases. Now, as we go from left to right, we're adding heat. And as we add heat, the particles speed up. And in class, I will show you, using the PhET simulation, how this can be simulated, where you actually, in the simulator, can actually see how the particles are actually increasing in speed. But when the substance gets to a temperature which we refer to as the melting point, it undergoes melting and then becomes a liquid. Now, it does take a bit of time. It doesn't just happen instantaneously, but over a period of time, at the melting point, the solid will change into a liquid. If we continue to heat the liquid, eventually it will reach a temperature, the boiling point. I use BP for boiling point, where it will now start, the bonds will start to break, and eventually it will become a gas. As we go from left to right, we can see that the speed of the particles is increasing. Here they're just vibrating, here they start to slide over each other, and here we can see that the particles are moving very fast by the length, the increased length of the arrows. If we remove heat, in other words, we cool it, we see that the gas becomes a liquid at the condensation point as it undergoes condensation. Remember, the condensation point is the temperature at which this occurs. The gas becomes a liquid, and eventually the liquid, when cooled enough, will reach its freezing point and become a solid. Now, for water, we know at sea level the freezing point is 0 degrees Celsius, but we also know the melting point is 0 degrees Celsius. So the melting point and the freezing point will always be the same value for the temperature, and the same is true of the boiling point and the condensation point. They will always be the same temperature. Now, certain substances like carbon dioxide and iodine, when you heat them, they will get to a point where they reach the sublimation point, SP, where they'll change from solid to gas. We will demonstrate this in class. And if you cool these gases, the carbon dioxide and iodine vapor, they will get to a recrystallization point or a deposition point where they will go from being a gas to a solid. So it is really very important that you are able to reproduce this diagram, because we will ask it in tests and exams. So in this photograph, I have a learner that's busy heating iodine crystals in a Bunsen burner. When the test tube is removed from the Bunsen burner and allowed to cool, we find that there are crystals that form on the top part of the test tube, which was cooler than the bottom part, which was being heated by the Bunsen burner. Here we can see that in actual fact, all of the iodine crystals have sublimated and have been recrystallized on the inside of the tube at the top part of the test tube, which was cooler. So initially sublimation took place at the bottom, and then recrystallization or deposition took place on the top. This is one of the very few apparatus diagrams we ask of you in the grade 8 course. We ask you to represent it and draw it in a test or exam situation. So firstly, you need a heading. So the heading would be the sublimation of iodine demonstration. You then draw the Bunsen burner. There, indicate the flame. At the bottom, we have iodine crystals. Then when it's heated, the iodine crystals become iodine vapor, and then that's the sublimation. And then when the iodine vapor reaches the top of the test tube, we get deposition or recrystallization where the crystals are reformed. So let's look at the labels. So if we look on the right-hand side, we can see that we have the test tube tongs, we have the test tube. Did I label the test tube? I should have labeled the test tube. I'm going to label the test tube because there should be a label for the test tube. Let me put that in. There is the test tube. We're not as fussy about labels as in life science, so our focus isn't on labels. So we will you'll be okay if you draw your lines and they're not exactly straight, and if your labels aren't exactly in line, as long as the label lines don't cross. So we've got the test tube, we've got the test tube tongs, we've got the iodine crystal. Now I want to go to the right here, and I want to show you that here the iodine crystals are represented with a capital I with a subscript 2 with an S. The S stands for solid, and the symbol for iodine is I2. We'll learn more about that later on. When it sublimates and it goes to iodine gas or iodine vapor, we represent the I2 with the G. And then when it recrystallizes, we represent the iodine crystals again as I2S. Right, the iodine crystals are a gray color, and the gas is like a purplish blue color. On the left-hand side here, you can see those little arrows there represent iodine solid to iodine gas, so that's sublimation. And these little arrows here from gas to solid, iodine gas to iodine solid, and that's deposition or recrystallization. So this is a very important diagram, and you should redraw this diagram in your books. So as an exercise, I would like you to take this template and use it in order to represent the various phase changes we have covered, including the sublimation and the deposition, and also including the actual particle diagrams of the solid, liquid, and gas phase.